Good day, gentlemen and ladies. Welcome back to class. In the last class, we treated some of the transducers available, and now we want to have a kind of revision of the last class, the last section of the last class. We are going to have it now. So I encourage you to pay attention to my screen and see what we did last. Okay. Okay. The transducer is used in motor vehicles to determine the level of fuel in the car that will be shown on the dashboard. There's a float in the gasoline tank of the motor car. There's a float switch there that is floating, that is actually determining the level of fuel in the tank. So that float works with a potentiometer that changes the current in the circuit. The tank is full till the white indicator on the dashboard goes to the blue. This there is minimum resistance and maximum current during the circuit. That is the simple method by which it works. Miriam, I don't know whether you have questions. I want to stop. You have any question? So that was the last class. Yes, ask your question.
Hello.
Hello, Miriam, ask your question. So that was the last class.
Flow transducer, is it the same as the flow?
So today we are moving on to the next transducer, that is the ultrasonic range sensor. Ultrasonic range sensor. So you pay attention now to the class and see my note on the screen. So to measure the level in a tank, a flow transducer can be used. But another way, another method that we can actually use is by employing ultrasonic range sensor. I know you are not coming across this for the first time. In EEI 311, we also made mention of floats and ultrasonic sensors, ultrasonic level measurements. Now, ultrasonic sensors use pulses of sound to measure distance. So the setup is such that you have a transmitter, which is also a receiver. So something that can transmit and receives. That is transceiver. So the transmitter, first of all, send out a pulse. The pulse is in form of ultrasonic signal. And then the pulse, the sensor is at the top of the tank. And then when the signal is sent, it's sent out towards the surface of the liquid or the fluid in the tank that is going to be measured. When the signal reaches the surface of the liquid, it is reflected back to the transceiver so that it can be received. Now, the transmitter sends out the pulse. Immediately it does that, it's also simultaneously initiate a timer circuit. And the timer circuit is to count the clock cycles to determine how much time is taken between the time when the signal is sent out and when it comes back and is received. So this receiver receives the reflected signal. That is the sound signal that is reflected back from the surface of the liquid. And the received signal is terminated. Immediately the received signal enters, the timer is terminated, and then the computation of distance is initiated. So a microprocessor will compute the distance based on the speed of sound through the medium, which is typically air. So such that you can now have two of the distances. When the signal is sent, it goes down, you take one distance to reach the surface of the fluid, and from the surface of the fluid, it's reflected back and it's received. So the signal will actually cover two distances. So those two distances, using the velocity of sound in air, typically, you can now calculate what is the distance. So the signal passed through a distance of 2d. So for that reason, the time taken will be delta t, and you can use this formula, this simple formula, to determine the distance, which is d equals 2v delta t, or d You know, velocity is equal to distance over time. Distance over time. Now, when you have two of the distance covered, then you can now say velocity is equal to 2d over delta t. 2d over delta t. So for you to get d will now be 2v delta t, as you see on the screen now. Now, when you look at this setup, you see the figure that shows this setup. We have the block diagram that represents this setup. We have a pulse generator. We have a transmit signal. We have a receive signal. We have a timer circuit. We have the control for the timer circuit, and then from the control, the data of the value of the distance is being sent out. So the pulse generator initiates the timing. When it's sending out the signal, it transmits the signal to the surface of the liquid and also tell the timing circuit to start at that point. So the timing circuit will start, and then the signal comes. You see the transmit signal comes, then the transmitter receiver send out the signal to the surface of the liquid. The liquid is reflected back and is being received by the transmitter. When the transmitter receives it, it sends another signal to the timing circuit to stop that the signal has entered. So you now see that the signal, the sound signal, has covered twice the distance d from the top of the tank to the surface of the liquid in the tank. And that is a simple principle of operation of the ultrasonic range sensor. So with that, we could have a very simple and accurate system of measuring the fluid in a tank. Very simple and accurate. You can see that it's not quite difficult to take the measurements by this setup, and it's going to be accurate because the microprocessor is the one that will take care of the value of the distance, calculating it, calculates the value of the distance to get d using the simple formula d equals 2v delta t, and that is a ultrasonic range sensor. Now we're moving on to velocity transducer. When you have question later on, when you receive the video, you can discuss the question later on. We are moving on to velocity transducers. Velocity transducers are used for speed control. And then we are going to describe two types of velocity transducer. The first one is the optical encoder, which is a digital instrument. And then another one, which is an analog instrument, that is VC tachometer. The two of them are the two velocity transducers that we are going to discuss in this class. The first one, let's look at the analog type, which is actually tachometer. The tachometer is simply using the principle of a generator, the simple principle of operation of a generator, the DC generator or AC generator that we already know, right from our physics time. We discuss about DC generator or AC generator. Even during electrical engineering science, we discuss this principle. It is the same principle that the tachometer is actually utilizing to generate the EMF that is used to take a measurement of speed or velocity. The device, as you see in the figure here, it has a, as you can see in the figure is down here. It has a permanent magnet that has a north and south. That permanent magnet is actually the stator. Then you have a coil made of wound wire that is able to rotate, and that one is regarded as the armature. This is the coil armature. At the end of the coil, we have brushes, carbon brushes, and then we have a slip ring that rotates with the armature. So at the end of these brushes, you can now take a connection from which we get a voltage developed voltage. So as we all know, this setup is such that we have a permanent magnet and you have a coil in between the permanent magnet. When the coil rotates, that is the rotating conductor in the magnetic field generated by the permanent magnet, which is the stator, then it cuts into the magnetic field or magnetic flux generated by the permanent magnet, and for that reason, EMF is induced in the rotating conductor. The rotating conductor, that is the coil, is mounted on the shaft of the device, which angular velocity is going to be measured. So the measurand, the quantity you want to measure will be the one moving at a particular speed. Then you mount the rotating conductor on it, rolling it at that same speed, so that the EMF developed will be dependent on the speed of the measurand, the quantity that we are going to measure its velocity. So that is the way it operates. So the rotating conductor passes through the magnetic field, and a current is induced in the conductor, resulting in a measurable voltage V out. Now, in an ID transformer, we can use this relationship to generate what voltage is being produced. And then this is V out divided by V in is equal to K. And K is termed the tachometer constant. K is termed the tachometer constant. V out over V in is equal to K. Is equal to K. So we see that it's very simple and straightforward to generate EMF by means of the rotating conductor. The EMF developed, the V out here, is actually dependent on the speed of the quantity being measured. The higher the speed, the higher the voltage developed. And so we can actually see that there's a relationship, a linear relationship between the voltage developed and the speed of what we are measuring. So we can actually determine the speed of what is being measured, what is the quantity being measured by means of this tachometer. So that's a simple way by which the tachometer actually produces EMF to measure the velocity of a body. Measure the velocity of a body. Okay, we can move on now to the next transducer in our course notes. When you have questions after going through this video, after listening and watching, you can actually send your question later and we'll discuss. But I believe this notes and the video here is explanatory enough. Now, earlier we have discussed optical encoder. Optical encoder, if you remember that, in our previous Zoom lecture, go and check the video on this page. We discussed this optical encoder that utilizes a photodiode or phototransistor to actually generate a signal, a V out signal, like a triangular wave like this. And the triangular wave is sent to a Schmitt trigger, which actually converts it to a square waveform like this. And that square waveform is actually what we can term as a digital output, digital waveform. It has on, off, on, off, on, off, depending on how the detector sees light. The photodetector requires light to produce an output, like you know, a photodiode or a phototransistor, that's the way they operate. So we can actually use this one also to measure velocity, because the disk is rotating based on the velocity of what you are taking, you are measuring. So that is what is going to generate the signal output, the voltage output. That is it. Now we are moving on to, we are through with tachometer. We want to look at force or pressure transducer. Force or pressure transducer. There are basically two types of force or pressure transducer that we are going to look at. We're going to look at a load cell, then we're going to look at strain gauge. Load cell and then strain gauge. Force sensors, basically, they are used in automatic weighing operation in industries and in robotic application, where it is necessary to actually control a given pressure. And then we are going to consider these analog devices, the load cell and the strain gauge. We have a typical example of application of a force or pressure transducer where it is being used. Well, let me give you a typical example. Some industries deal with buying quantity of certain material. For instance, if you see some large trucks, they carry granite, stones around. Some of those quarries where they sell this granite to them, they weigh the vehicle and then empty vehicle, and then when the vehicle is coming out, they weigh it again to determine the quantity of the granite that has been, dumped into the vehicle, into the truck. So you use this kind of system to determine the weight of that truck. So we have a device. The device will be on the road or at the gate where the vehicle will pass through to enter, to go and collect the granite and come out again. So the empty vehicle will climb on top, is check the weight. Then they will now dump the quantity of granite into it, whether 5 tons, 10.5 tons, 10 tons, 15 tons, whatever. The vehicle comes back and climbs the weighing scale. When it climbs the weighing scale, then the weight will increase. So with that, they can determine the quantity, how many tons of granite has been dumped into the truck. Likewise, some depots, fuel depots, maybe diesel, gasoline, kerosene, they use this kind of system also, whereby the empty truck will climb on the weighing scale and enter to the depot, and then collect the fuel into the tank and come back and climb it again. Then they now look at the total weight. Total weight minus empty weight will give the total quantity of the fuel that has been put into the tank. So we have two transducers that can be used to, construct such weighing scale. One of them here is what we have under 1.2.3, load cell. The load cell is used in processes where precise weighing is required. And then a load cell can be implemented using LVDT or a strain gauge. A strain gauge, like you all know, is a force transducer. A force transducer, pressure of force transducer. And LVDT is actually an inductive transducer that converts, position into a change in resistance, kind of. So in the figure here, we have an example of load cell that is implemented using LVDT. So we have a load cell implemented by LVDT and with a spring, its linear force displacement relation. You see the helical spring here. The helical spring is that is where the load will be attached, and then when the load is attached to it, it draws the helical spring, and that when that happens, then the force can be measured using this transfer function. F equals K delta D. F is the force exerted on the spring. K is the spring constant. And then D, delta D is the displacement from the unloaded rest position. When there is no load attached to this helical spring, the spring has a length. But when a load is attached, you will discover that the load will pull the string and extend it. So we now have a displacement from the resting position to the position the load extends the spring to, and that is what it gives delta D in this formula. So we have an example to demonstrate this calculation. We have an example here. A load cell using a strain gauge is subjected to a pressure of 10 kilonewton on an effective area of 1,200 millimeters squared. If the material used for the strain gauge has a spring constant of 0.5 Newton per millimeter, determine the cell displacement. Now, what we now realize is that the force is related to pressure and area. We already know that right from our secondary school day, that pressure is equal to force divided by area of a body. Now, when you can measure force, then definitely you can actually measure the pressure exerted by that force on a body. So let's check this. The calculation goes thus. Force can be gotten from this formula, P equals FA. So force, therefore, equals PA, pressure multiplied by the area. Now, in the question, we are told that the pressure is 10 kilonewton, and then we are told that the effective area is 1,200 millimeters squared. What you need to do is to convert the millimeter square into meter squared, and that one is done by multiplying by 10 raised to the minus 6. So 10 times 10 raised to the 3, that is F now. F equals 10 times 10 raised to the 3 multiplied by 1,200 times 10 raised to the minus 6 gives us 12 Newton. 12 Newton. Now, this 12 Newton now is the force. Now, in the previous formula that we encountered, we said F is equal to K delta D, and we are told to determine the spring displacement, which is delta D. So therefore, delta D equals F divided by K. Delta D, as you can see on the screen, equals F divided by K. That is 12 Newton divided by 0.5. We are told that the spring constant is 0.5 Newton per millimeter. So we have 12 divided by 0.5, that is 24 millimeter. 24 millimeter. So you can see that this is straightforward. If you check the past question, you see this question coming in another format, not in the same format, but using the same formula. I think I also gave an assignment. I'm not sure whether I've given you this assignment, whereby you solve. Instead of calculating the spring displacement, you can calculate force, you can calculate the cross-sectional area using the same set of formulas that we have there. So that is that. Now, that is how load cell is being used. Load cell, implemented using LVDT, as we have here. We have LVDT, we have the force being applied to the spring, the helical spring of the load cell, and we have the support here. So the core of the LVDT is where the force is being applied, and that is attached to the helical spring. So the force can be calculated from the formula F is equal to K delta D. F is equal to K delta D. It's simple and straightforward. When you have questions, you will let us know later. Okay. We're moving on to the next one, which is a strain gauge. Strain gauge. Now, the strain gauge is the most widely used pressure and force transducer. Pressure and force transducer. The most widely used is the strain gauge. And the principle of operation is based on the resistance property of an electrical conductor. We know that an electrical conductor possesses a resistance based on the usual formula that we know, that we see on the screen here. R equals rho L divided by A. The resistance of a conductor depends on the resistivity, the length of the conductor, and also the cross-sectional area of the conductor. Now, when you change the cross-sectional area of the conductor A, then the total resistance will change. And that is why a conductor, a small wire, and then a bigger wire of the same material will not have the same resistance. Even if they have the same length, they will not have the same resistance. And that goes to tell us from this formula the effect of cross-sectional area on the resistance of the conductor. Look at this for instance. When we have a small wire, we discover that small wire, what we're dealing with will be the cross-sectional area. The small wire, we have a smaller cross-sectional area. The bigger cable, we have a larger cross-sectional area. So when you look at this formula, you see that the resistance you will get with a small wire will be bigger or larger than the one you will get with the bigger cable. So you see that this formula goes to tell us that the length, when you increase the length, the resistance will increase. When you change resistivity, probably increasing resistivity, the resistance will also increase. If you change resistivity to a lower resistivity, then resistance reduces. Then if you change the cross-sectional area by increasing A, for instance, resistance reduces. That is when you increase the size of the cable, the cross-sectional area of the cable, the resistance drops. But if you change to a smaller cable by reducing cross-sectional area, maybe the cable with smaller radius or diameter, it will give higher resistance, even if the material is made of the same material and has the same length. So that is what we have. The resistivity is determined by a particular type of material, whether it's copper wire, aluminum, or whichever material you are using. Different metals have different resistivity, and it's constant for each type of material, measured in ohm centimeter. L is the length of the wire measured in centimeter or meter, and A is the cross-sectional area measured in centimeter square. You can change this one your note to centimeter square. It's not cm2, but cm squared. The resistivity is constant and then can be changed by when you change the material. You change in length, you change in cross-sectional area of the wire, A change in resistivity can cause a change in resistance. And this phenomenon is called piezoresistivity. Piezoresistivity. In your exam, you can be asked to explain the phenomenon called piezoresistivity as related to, strain gauge. Piezoresistivity. You should be able to explain this. So strain gauge is operating on the principle of R is equal to rho L divided by A. In EEI 431, we looked at the related calculation, how strain gauge work on the resistivity of the material or resistance of the material, and also on the Hooke's law. Because Hooke's law tells us that when you stretch a conductor, when the elastic limit has not been reached, then the force you apply is proportional to the increase in length. Increase in length. So when you drop the load or the force on top of the conductor goes back to the original length, given that elastic limit has not been exceeded. But when elastic limit is exceeded, there will be plastic deformation in the material. The material will be deformed, and then it will not go back to the original length. Then the length will now be longer or higher than the original length. So we look at that in 431, if you could remember, and then we derive the necessary formula. We are not going to bother ourselves with those calculation right here. We only want to know the principle of operation of the strain gauge. The strain gauge works in a way that when you apply pressure, then the strain gauge changes its resistance. When you apply pressure or force on it, then the resistance of the strain gauge changes, whether increasing or decreasing in resistance. And so, as an engineer, you know that if you can achieve a change in resistance from a transducer, you are so happy, because that will be good enough to calibrate in a circuit where a current is passing. When there is higher resistance, the current drops, it reduces. When there is increase in resistance, the current drops. When there is reduction in resistance, then the current increases. And then you can calibrate a meter moving, reading these currents to indicate measuring maybe a force or pressure, depending on what you are looking at. So it's very easy for an engineer to calibrate his device, measuring force or pressure using the strain gauge in that manner. Now moving on to the next one, which is thermocouple. Thermocouple is what is nothing new to you people again. Now for the last instrumentation and control courses, we treated thermocouples. EEI 311, we dealt with thermocouples, which is actually a temperature measuring transducer. The same way in EEI 431, we dealt with transducer. Over there, we also we look at more things regarding the transducer, which include the loss of thermocouple, loss of intermediate temperature, loss of this, loss of that, every loss of thermocouple. But basically, the principle of operation of a transducer is what we're going to revise here. The transducer is used to measure, change in temperature. And then the material is constructed using two dissimilar metals, two dissimilar wires that are bonded together at one end. That bonded, they say it means it is probably welded, soldered. They are just connected together electrically at that point. And that point is called the sensing end. Now, when you put the sensing end at a change at a higher temperature, and then there's a reference, junction, you now discover that the two free ends of the wires will produce an EMF. An EMF will be produced. Why is that happening? Because two dissimilar wires joined together at one end, the electrons will be flowing in the wires at different rates, even though they are getting the electrons from the same junction, but they move at different rates. For that reason, there will be differences in the molecular structure. Because of the differences in the molecular structure of the material, there will be a gradients in the movement of the electrons, and that is what constitutes the EMF generated. Remember, electromotive force. You can say electromotive force, driving a current in a circuit, because there will be a potential gradient. So there will be a potential gradient between the two ends of the wire, because they are not made of the same materials, the potential gradient, and that causes a generation of EMF. And this is what is shown in the figure that we have here. It's not different from the figure that we had in EEI 431 and 311, but it's drawn in a way, in a different manner. We have a sensing junction where the two wires are joined together at temperature T. That is point A. Then we have metal A, which is copper. We have metal B, which is nickel. The two of them are joined together at point AA. Then we have a reference point. That is a temperature controlling junction, which is point B. Now, the signal that is coming from the two wires at this end, at this other end, that where we have signal out, where we have copper wire here, we have nickel here, but we now use copper wire to lead them out after the TREF, is the temperature control reference junction. The temperature control reference junction will be maintained at a particular temperature, and so there will be a difference between the T at point A and TREF. For that reason, EMF will be produced at the points where we have signal out here. At the point where we have signal out, EMF will be produced. So that's the way the thermocouple works. So the EMF produced, voltage out, can be, is proportional to the difference in the temperature. It's proportional to T minus TREF. So you can see it in the formula on the screen. There will be a small current that is flowing in the cables, thereby producing EMF at the two ends of the two wires. So we have V out equals alpha T minus TREF. The alpha here is actually the constant in volts per degree, K, and the T and TREF are the measurement of temperatures, the temperature we are measuring and the reference temperature respectively. Alpha is a constant. The alpha has to do with the type of material used for the two wires. The type of material used for the two wires. So we can actually calculate the EMF generated by the thermocouple. And we calculated, this is something that you are familiar with already. You are very familiar with the calculation under thermocouple. The calculation is in 311 and 431, we have touched the calculations. So we do not want to bother too much now with this calculation again. Of course, we can do the calculation again based on the formula that we have here. And that is how we can use thermocouple to measure temperature. So the temperature being measured, which is actually T minus TREF, is proportional to the EMF that is produced. So therefore, because there is a proportionality, although it may not be totally linear proportionality, but there's a proportionality, in the relationship. So it can help us to calibrate the device and measure the current that is being drawn out by that EMF and calibrate it as the temperature that is being measured. What really happens here is that we have a conversion of energy. Energy is being converted from one form to the other, from thermal energy or heat energy into electrical energy. So there's the conversion of energy that's taking place on the temperature that we are measuring to the EMF that we are producing from the thermocouple. The thermocouple helps us to do a conversion of energy. And remember, that is why we define thermocouple also as a transducer. Because a transducer helps us to convert energy from one form to another. So this is a temperature transducer. That's a temperature transducer. I hope this is very clear. I hope this is clear. Okay, it's explanatory, but when you have questions later on, we can actually handle your question. You can log on to the portal, and then under chat room, you can throw up questions there. Let me know if you do that. I will open the chat room and answer your questions over there as well on the portal. Now, we're going to move on to another subheading, resistance temperature detector, RTD. Resistance temperature detector, RTD. RTD is another means by which we can actually measure temperature. We can measure temperature using RTD. Okay. RTD, as the name implies, is resistance temperature detector and is based on a particular property of metals, whereby when you increase the temperature of metals, their resistance changes. And then you see that metals have a positive coefficient of resistance such that when temperature increases, the resistance increases. As temperature increases for metals, their electrical resistance increases. The reason being that higher temperature in metal results in vibration of electrons. It's not a generation of more electrons, but vibration of electrons. And this vibration of electrons impede the flow of free electrons in the metal. For that reason, the resistance of the metal increases. You know, this is a converse relationship to what happened in semiconductors. Semiconductors, when you increase their temperature, they generate more, the temperature liberates more electrons in the semiconductor, and those more electrons vibrated, they are now carriers. They can carry, electric currents through the semiconductor. For that reason, the resistance of semiconductor decreases when you increase the temperature. Unlike in metal here, where we have temperature increase resulting into increase in resistance, because rather than generating more electrons in the metals, it results into the increase in temperature results into vibrations of the electrons in the metals. And this vibration causes an impediment, impedes the flow of free electrons in the metals. For that reason, the resistance of the metal increases when you increase its temperature. Now, based on the same formula that we use up there, which is resistivity, resistance is proportional or equal, resistance equals to rho L over A. I'm still using the same formula here. Resistance equals rho L over A, where rho is the resistivity of the material being used, whether it's aluminum, copper, or whatever metal. Length, L is equal to the length of the wire in centimeter, and A is the cross-sectional area of the wire. So you can see that here, rho, which is resistivity, is a temperature-sensitive parameter. A temperature-sensitive parameter. When you increase temperature, the resistivity of that material, which is a metal, changes. Resistivity increases. For that reason, the resistance of the metal increases. So with our knowledge of the relationship between rho and temperature of a particular metal, it is possible for engineers to construct RTD with a particular relationship between R and T. So that is what RTD uses, the principle of increasing resistivity of a metal when temperature increases. So RTD is constructed based on this principle. Change in resistivity of a metal with changes in temperature, with increase in temperature. So we construct RTD based on this principle. It's a specific relationship between resistance and temperature, so that as temperature increases, resistance increases. So for that reason, the device is used to detect increase in temperature. That is why they call it resistance temperature detector. Resistance temperature detector is detecting changes in temperature based on changes in resistance. And that change of resistance is caused by a change in resistivity of the metal used in the device. That's very simple and straightforward principle of operation of the RTD, resistance temperature detector. I hope this is very clear because we're going to move on now. I know this is very clear. It's simple and straightforward. It's clear. But if you have questions, later on you can post a question on the portal, on the chat room there. You can actually answer that from the portal. Now we are looking at another transducer for measuring temperature. That is thermistor. Thermistor. A thermistor is basically another device that can measure temperature. But now, the thermistor is usually composed of a semiconductor or some other metal alloys. The thermistor is made of semiconductor material that exhibits a predictable change in resistance as temperature is changed. Yes, like I've explained just before now, the semiconductor changes its temperature. A change in temperature of a semiconductor causes a reduction in resistance of semiconductors because higher temperature causes higher charge carriers to be developed inside silicon or probably germanium. And so, for that reason, the molecular structure of a semiconductor is such that increase in temperature reduces its resistance. Increase in temperature reduces resistance in semiconductor. So as the temperature of the material increases, more electrons are break from the covalent bonds, and so you now have increase in charge carriers that results into higher conductivity of the material. And this is the formula that relates this situation that happens in semiconductor. RT equals R naught exponential beta raised to power 1 over T minus 1 over T naught. Now, what is RT? RT is the resistance of the temperature of the thermistor at a temperature T, the capital T we have here, capital T here. So that is the resistance of the material. RT is the resistance of that material at temperature T. And then R naught is the resistance of that material at another temperature T naught here that we have here. So that is the resistance that corresponds to that. This resistance R naught corresponds to this temperature T naught. T naught. So the T is the point, the temperature that we are going to take measurements, the temperature that we want to know. Whereas the temperature T naught is a reference temperature. Both are measured in Kelvin. Both are measured in Kelvin, degrees Kelvin. And beta is a property of a material used to make the thermistor. Beta here is a property of the material used to make the thermistor. So the formula up here will be used to determine the resistance that the thermistor will generate based on the change in temperature that we are measuring. The temperature we are measuring will be temperature T, capital T there. And then the reference temperature is used to determine that. So this is an exponential equation that can be solved and you have the necessary parameters. Okay, so the nonlinearity of the thermistor is response function. It's used to be limited only over linear range of the device. Look at the formula up here, you see that this is a non-linear equation. It's not something x times y plus z times something. It is something raised to power something exponential, and that's a non-linear function. E raised to power beta bracket 1 over t minus 1 over t naught. So that is why the application of a thermistor is limited to certain areas because of the non-linearity. So we have tutorial here. We have tutorial question that we can go and practice and answer it. Differentiate between a resolver and an encoder. Differentiate between a resolver and an encoder. Now, what is the difference between a thermocouple and a thermistor? What is the difference between a thermocouple and a thermistor? We have just gone through that now. We can explain the principle of operation of each one and show the difference between the two of them. A resolver too and an encoder, you can differentiate between them. They're working in different principle of operation. Yes. So that is about the temperature transducers. I think that is very clear and straightforward. If you have question, you can get your question down across to me through the portal. Log on to the portal and then answer put down the question there. And then that reminds me, we gave an assignment on the portal, and I think the deadline The deadline is, I think it's over now. I'm not so sure the deadline for the submission. Some of you have submitted. I think maybe one or two person has